Hi and welcome back everyone for today's evening session. The first talk this evening will be by Professor Deepankar Banerjee. He is the director of ARIES and also a professor at the Indian Institute of Astrophysics. And he will be giving a talk on Aditya L1 mission and the activities of the support cell. So if you have any questions during the talk, you can raise your hand or ask them, uh, or you can also type your questions in the chat box. And Professor Banerjee will be intimated if the questions are in the chat box, or you can ask them later on after the talk as well. So uh, we'll start now. Over to you, Professor Banerjee.
Yeah, thank you, Om, for inviting me. Good evening, everyone. Let me first try to again share my screen and ensure that everything is in order. It's coming up, I presume. And if I go into full screen mode, you just confirm me that you see the first screen
Yeah,
in the full screen, right?
yes, we can.
Okay, okay. Thank you very much for inviting me to give this, talk. I understand the theme of the meeting is somewhat, different, but what all you are doing for this different techniques which you are expected to learn is for big data, and we have these new fantastic opportunities within the country for generating big data. Uh, so. Uh, so I'm just giving you some exposure about this forthcoming mission, which is called Aditya L1, India's first space observatory to study the sun. And to increase the user community, we have set up rather ISRO in collaboration with ARIES Nainital have set up a Aditya support cell. And actually this week we are having the first support cell workshop. Unfortunately, that clashed with this workshop at Kolkata, so I couldn't be physically be present at Kolkata now. Hopefully, in near future, we'll be seeing each other and will be able to exchange our ideas. So, thank you for this opportunity to come closer to all of you. The other point I want to raise is I'm seeing my full screen, so I am not seeing anything else. So if somebody asks questions or raises hand, Om, please help me out, and don't hesitate to just interject and then ask or prompt the question for me, please.
Okay,
Okay.
sure.
So this is the solar space observatory, which is going to be launched hopefully by end of this year or probably first week of first half of next year. Because of the pandemic, we got slightly delayed. This is a multi-institutional project. There are 7 payloads. Payloads are these instruments which are being built at different parts of India, at different laboratories across. So I won't be able to probably give a comprehensive list or full account of all the instruments in full go, but I will try my best to give you a flavor about the different instruments and their capabilities and so on in a sort of basic level. So as you see here, there are multiple institutions logo. They're participating in this overall exercise, either in building instrument or being a part of the science team. And on behalf of the science working group, I'm here to make this presentation. So before I go to a solar mission, it is there are two important elements to understand about modern day astronomy. One is the question of multi wavelength. Why do we need multi wavelength? And in that context, actually, you will probably realize that why do we need to go to space? And the other big question is today I'm going to talk about only a solar mission, but Sun is our nearest star, and it is our closest astrophysical object, what we can study in such greater detail. So at the end of the day, we are astrophysicists, and we should, you know, uh, put our solar physics in the context of the larger picture, which is knowing the universe at large. and that has all these constituents from stars to galaxies to extragalactic sources and beyond. So here I'm showing our overall national mission, what we have. So in this place, you see the wavelengths, as you know, from the shortest of wavelength all the way, if you go to longest wavelength. Some of the wavelengths are accessible from the ground, but shorter the wavelength, it is harder to be observed from ground. Although having said that, there are certain experiments from the ground also, which is possible. So these are all from the Indian context. We are showing that these are operational, observing facilities in shorter wavelengths, mostly from the high altitude sites. These are, optical telescopes. Of course, the largest of these telescopes from India is situated at Aries, the Westhill campus. And you have the longer wavelengths, the radio wavelengths, the UT and the GMRT and Gauri Bidanur host, fantastic, facilities. And on the right side, these are the planned mission, what you can see here. And Aditya L1 and XPOSAT, these are the two major new missions which are expected to be flown, as I said, within next 1 year. And I'm only going to talk about this, but then you have Diksha mission, you have INCEST. This is a UV payload under, in the early phase of its development. And again, these X-ray polarimeter, exovolts, these are all more in the conceptual phase, but more likely to be in space in these timescales of 2030 to 2035. Apart from this, there are also India is part of many international programs, and this is what is listed here. You name it: 30-meter telescope project, square kilometer array, LIGO India, and thankfully we are all part of this. Why I'm showing this, diagram is all these projects and missions are going to generate huge amount of data, and we will not have any possibility of looking at these large volume of data selectively. Even to select, there has to be some criteria why we select this data. So we are going to be heavily dependent on automation and computing, power resources. So this particular workshop, which has been, organized and at ISA Kolkata, I really very much appreciate. It's very timely that the entire community has to be prepared for these kind of major missions. So it's not enough to build instruments or to participate in international projects unless you are ready for it. How to handle the data, and handling the data for doing the second step of doing the science. So I think this is very timely, and these missions are all going to generate big data. And to be honest, probably astronomy can boast of being ideal platform for big data science, apart from biological sciences and other environmental sciences and so on. So I think we have to, or the next generation have to be prepared with this automation. And I thought, I will just impress on you how important is this kind of workshop and training going to be for our near future even. So here I will just list out the different payloads on Aditya L1 mission. Again, as I mentioned, since I am not sure how much solar physics knowledge or exposure is there with the participants, and virtually when I give a talk, it becomes even more difficult for me to assess this. If I look at your eyes, then I can make out whether it is making any sense. That opportunity is also lost in this virtual mode. But I will try my best to give you some information. I will share my slides if you like, and then we can have subsequent interactions or exchange of emails and so on to take it forward. So I hope you will bear with me, because in 35 minutes or 40 minutes, I will not be able to really do a good justice for a mission of this scale. So this is a coronagraph. Coronagraph are devices which looks at the extended atmosphere of the sun. This is the solar corona. And again, as I mentioned, modern day astronomy demands that you have multi-wavelength capabilities of a mission. So here in the coronagraph itself, we have through three visible channels, three different cameras, and one infrared camera. We are going to look at different layers of the atmosphere of the sun, um, primarily from the VLC, the coronal heights, but the SOOT instrument, which is a near UV full disk imager, it will have possibilities of using different filters, and different filters allows different wavelength pass bands, and that mimics or pictures different layers of the atmosphere of the sun. So there is this photosphere is the visible surface. Then you have chromosphere, which is about 2,000 kilometers, called chromosphere, and then the higher up in the atmosphere beyond chromosphere is called the corona, which extends to very very many solar radial distances away. So these are also called remote sensing instruments, because I will be talking about that this Aditya L1 mission is going quite far. We are going to reach L1 point, which is about 127,000 kilometers away from Earth. This is again a fantastic, attempt, I would say, because apart from NASA and ESA, nobody has been able to reach at L1 point. So this is again a technology demonstration for our space commission as well. So apart from these two imaging and spectroscopic instruments, we have two particle experiments. One is called Aditya Solar Wind Particle Experiment called ASPEX, and the other one is called PAPA. So once we reach L1, the idea is that you are basically about 1% distance between the sun and the Earth line, but you are able to continuously look at the sun, and so you can take images or spectral informations of emissions which is coming from the sun by remote sensing. Also, you can have in situ instruments. So these particle detectors are basically in situ instruments, because anything coming out of the sun in terms of its radiation and particles and the mass, if it travels in the interplanetary space, it has to pass through the satellite if it wants to reach Earth. So in that process, we'll be able to probe the properties of these particles in its charge states and its mass and energy, and then its magnetic properties and so on. So that's the idea of combination of having remote sensing instruments and particle detectors or in situ instruments. So apart from this, we also have two X-ray payloads. These are X-ray spectrometers. Primarily, we will be looking at very dynamic, events which happens in the sun. They are called the flares, and these flares, emit lots of energetic particles and mass and so on. So it's very important to study these flares and study their properties and characterizations and so on. Will be done with these two X-ray spectrometers, and we will have a magnetometer which will be sitting at the, as I mentioned, at Lagrangian 1 point to, characterize the measure the magnitude and nature of the interplanetary field and these particles which are coming, carrying. So this is a start view of the Aditya L1 satellite. As you can see, the coronagraph is the biggest, payload in this suite of instruments. It's sitting in the top deck. And by that side, the near UV imager, which is built at IUCA, currently at ISRO in the assembling stage and the final testing phase. They are sitting side by side at the top deck, and other particle detectors and the X-ray spectrometers and all that are shown at different locations of this satellite. And when it is deployed, of course, the solar cells will wide open, looking at towards the sun, which will provide all the energy requirements for operations. So this is what the L1 location is, roughly about 1.5 million kilometers away. It will take about 109 days to reach there, and straight away one cannot reach Lagrangian 1 point. Even if you are aware of Mangalan mission, it goes something like this orbit, Earth-centered orbit with increasing the ellipticity, and then eventually it will try to leave the Earth's gravity, and then this is called the cruise phase, and then eventually around the Lagrangian 1 point, which is one of the stable points in a three-body systems in a three-dimensional environment, it will be doing a huge elliptical orbit circulations again. The advantage of the Lagrangian one point is also that once we reach at L1, although we are making a huge orbit around L1, it needs only very less amount of energy, because the gravity between the satellite and the Earth balances the force between the satellite and the sun. So that's how it needs a very, very little fuel to remain in that particular orbit and all that. So as I mentioned, so this is the set of instruments: coronagraph, the imager. These two are the X-ray spectrometers, and these are the particle detectors and the magnetometer. Of course, as you can imagine, that this mission with so many payloads will have lots of scientific objectives and science questions to be addressed. And unfortunately, I will not be able to do a full justice to tell you about all this. It will not be fair, and probably a very incomplete exercise also. So I will try very, very few salient features of some of the payloads, which is for the first time we are going to look at. What is shown here is a perfect eclipse image, which creates a first view of the corona, which is the best one can have. But as you know, the total solar eclipse is very rare, and you have to go to very different places, and weather conditions also may not be favorable to see this. So for regular observations and all that, we are dependent on this kind of occulter. These are called the coronagraph. So ground-based coronagraphs are there, which can look at very close to the limb, but because of the atmospheric conditions and a lot of scattered light, these again are quite a difficult thing to achieve from the ground. There have been attempts from space. This was there, C1 coronagraph at Soho, but unfortunately it operated only for 2 years between 96 and 98. So we do not have such a inner coronagraph, in space right now. There's been attempt later on also, but there have been challenges, and we do not have regular observations of the inner corona. This is the other coronagraph. As you can see, it is blocking up to 2.5 solar radii. So you see the extended part of the corona, which is also important, but we are missing information from the inner corona. So that's why the inner corona is very, very important, and Aditya coronagraph is going to primarily look at that. So this is the field of view of the coronagraph, which very nicely shows all these different coronal structures. And these coronal structures are very dynamic, they change with time. They're not always, of this shape and size and dimensions. They are very dynamic features. So it's important to be able to observe them continuously with a very high, cadence. That means, high frequency of observations and so on. So apart from this image, we also have a spectroscopic experiment and two spectroscopic channel. In fact, two visible spectroscopic channel and one infrared spectroscopic channel, which will allow us to characterize the properties of the plasma from the corona, its its temperature, its density through some modeling, and then again the magnetic field, how it is configured, how it is structured, how its strength can be at different parts of the corona. So all these things will be probably for the first time with such a kind of precision we will be able to look at. So there are some unique elements of this. So this is just a enlarged or zoomed portion of this to sort of also emphasize that how nicely we'll be able to study these different structures, whether it is in the equatorial region of the sun. These are called helmet streamers. So in this streamer structure, when these streamers are there, what are the properties inside the streamer or outside? These regions are in the polar region. They are called polar plumes, through which the continuous expansion of the outer atmosphere of the sun in terms of the solar wind happens. So we will be having possibilities of measuring the solar wind very close to the sun with such better precisions as compared to the existing data. So CME observations are, as I indicated, that in the past, because of the C2 coronagraph, which is there for the last 20 years, is producing every day lots of data, but this is the missing area. So this is the C2 coronagraph. Then you have on disk images, but this is the place where we have lots of information which is not available. So a combination of this yellow circle, which is our field of view of Aditya coronagraph, and the spectrographic channel will fill up a lot of information about these CMEs. So this is called a CME. I hope most of you are familiar with this object called coronal mass ejection. Whenever there is a huge explosion in the atmosphere of the sun in the form of a flare, or a huge instability eruptions in the terms of a prominence, then this leads to this kind of huge amount of mass ejected in the interplanetary space called coronal mass ejection. And to characterize the properties of the coronal mass ejection, tracking them and so on will be very much possible. We'll have a large possibilities of different exposures. That means, you have possibilities of tracking these objects with, very high cadence. As I said, if every minute you will be able to take one images. So it will contribute to the imaging in the white light counterparts identification. Often what happens is within the CME also, different parts of the CME moves with different speeds and so on. So better accuracy, better data will allow us to study this term called velocity dispersion within CME. CME tracking from the inner corona, because as you see, this is a good example of actually a ground-based coronagraph. Such examples are not there many because ground-based coronagraphs are not all the time operating. So here is a case, actually, this is a prominence which is erupted somewhere in the close to the limb, and then this prominence has given rise to this CME, which is very nicely followed by C2. But in this region, we have limited data, and if we get a regular observations from space, that will help in our understanding. So here again, as I mentioned, this is typically a X-ray, a curve. What it shows, the continuous curve is depicting how the X-ray flux increases with the time. So here, this is time, and then this is X-ray flux, which is plotted here. And these particular data points are the velocities as measured from the different coronagraphs, C1, C2, and C3. And as you can see here, C1 had these, few data points. Then C2 allows you to study these data points, and this is C3, these two. So combination of different coronagraphs allowed us to, follow these different portions of the CME as it propagates between the sun and the earth, and that corresponds to different phases of the flare. And one, in the terms of a flare, one depicts a pre-flare phase. That means, because just before the huge explosion, there are certain development phase, which is called the pre-flare phase. Then this is called the rise phase and the decay phase. So this is the peak time where the flare has occurred, and that has a direct correspondence to the different phases of the propagation of the CMEs as well. So to properly study, as you can see, that better your data are, in this region, more closely packed, you will be able to study them much, much better. And as I indicated, the C1 coronagraph is not there in space for the last 20 years. So this is an example of how nicely C1 did capture, but we don't have such data available now to improve on this understanding as well. So there's a huge lack of our understanding are confirming this. And this region also, as you can see here, there is huge data gaps because of the cadence. Means, your two images are separated by several minutes or tens of minutes. And if you have a possibility of taking many frames within a minute, then you can imagine how many data points you can have within this, to capture these things much better. So that is a sort of impression people have could be the resultant picture. And the resolution of this, of course, the images are also pretty poor, and we will have a much better resolution, which will allow us to sort of see these CME. CME also has different parts or different components. This is called the leading edge. Then you have a void area, and then there is a core area, which is sometimes a prominence material and so on. So to capture all these different parts of a CME also is crucially dependent on the resolution of the detector what you have. So all these are going to be much more improved. We will have images. This is shown an image of, of the corona 2006, 2008, 2009, and 10. And you see the corona is how dynamic it is. And if I take filtered images of different, with color, then you will see, different parts of the corona, how evolving it is. So continuously, once we are at L1, we'll be able to take it in every day, every minute, such images to study the dynamics and the thermal properties of corona and so on. Of course, that needs theoretical models. This is a model which is developed at SESI in Kolkata, where this workshop is being held. So SESI is very, created expertise in the magnetic, structure of the corona. This is a global field, modeling, which is, very much important for our understanding of the CME or any ejecta, how it will go. It crucially depends on the magnetic field structure of these elements and the background where it has to propagate through. So these are again beautiful results which has come out of CESI's simulations. Again, it's a unique example how we have to work together. This is again another example how detailed these coronal structure models were, and how nicely it can constrain our understanding, and a comparison of our observation and with these theoretical models will take us to the really next level of science. I have to probably rush through, or will skip few slides and come to the user center, because I'm taking much longer than I was anticipating. But nonetheless, let me just tell you that I mentioned about the coronagraph, and this is the other payload, near UV payload, which will map different layers of the atmosphere of the sun. Primarily, majority of the space imaging devices are there in this region, in the higher part of the corona. But in this mission, we will be mostly focusing on the lower heights. Typically, to these heights in the solar atmosphere, what is shown here is the temperature as we go away from the sun. You see that temperature is more or less at a temperature value of tens of thousands of Kelvin, and suddenly temperature goes into millions of Kelvin in the corona through a transition region. So we're going to focus from the suit instruments these layers, probe these different layers, and study the dynamics and so on. I think I will skip a few slides, and because I'm short of time. So I will just mention that these are two X-ray payloads, which we have, one in the low energy and the other one in the high energy. So this is the energy spectrum. So when you have different energy resolutions and different energy bands detectors simultaneously, it will allow you to probe the development of the flares. So how the energy is released, how the particles are accelerated at different phases because of the different energy requirement of different processes, what exactly triggers a flare and any eruptive phenomena. And then there are certain times there are thermal emissions, there are certain times there are non-thermal emissions in terms of its flares evolution and so on. So that will be all studied from these two X-ray spectrometers. We have two particle detectors. So essentially, as I mentioned, that the solar wind is the continuous expansion of the sun, with lots of particles and electrons and ions of different charge states. So to probe their properties, this is going to work in this particular energy range, and aspects will have a possibility of complementing these energy ranges. It will look at energy distribution of different particles from 100 eV to 20 keV. It will also do a charge ratio number density to different solar events, like as I mentioned before flare, after flare, or if there are different classes and sizes of flare as well. How does this affect the particle density, and how does it change its propagation within the CMEs and so on, will be studied from these two particle detectors. So these are the different, again, ranges. So we will look at solar wind. Incidentally, the solar wind is also not very uniform. there are certain regions of the sun, primarily from the equatorial region, the slow solar wind comes with a velocity of 200 to 300 kilometer per second, whereas for high latitude and the polar regions, we have the fast solar wind with velocities even of the order of 700 kilometer per second. So it carries different energy ranges as well in terms of its particle constituents. So study their properties and so on will be done through this way as well. And then finally, we have a magnetometer, which will be sitting and looking at when there is a CME which is passing through the satellite. It will has to pass through the magnetometer, and then it will try to detect the magnitude and direction of these CME components of magnetic field, because that's very crucial when it comes close to the sun. So I will again skip some of these particular aspect that you have to realize that when we have such a suite of instruments, that these instruments has to talk, work in conjunction. Then only we get the complete picture of a CME, how it is, generated, how it is propagating, and what kind of impact it can do when it comes to our environment. So this is a subject area where again SESI is building expertise, and there is a space weather prediction center based on looking at the sun, the flare, the classes of the flares, and all that. So it's a composite system now. Sun is not studied in isolation. It is studied in the heliophysics context, and the sun-earth interaction. In fact, sun other planet interaction is also very, very important. And this is again something which is happening at SESI Kolkata. So these are different, kind of effects of these radiations and the masses which is coming off the sun in our, near Earth environment in terms of our communication systems, telecommunications. If there are space, craft. Recently, there were, SpaceX experiment, which was a complete, loss because of the atmospheric drag, and the orbits were, altered, and that led to disasters of this. And of course, our modern technology is very much dependent on the radio wave, communications and GPSs and so on. All these gets affected by these, huge impacts, which is because of the sun and solar disturbances and the solar storms. So this is a area again will need lots of data, and it's assimilation. This is again a simulation which is from your SESI's group about in situ can enable the data-driven sun-earth interaction model. I'm just sort of giving an overview of the kind of different things in the solar context which will generate a huge amount of data, and we need to build this user community. For that purpose, this science support cell has been done here. So this is the science support cell will look at data utilization and training for all these payloads which is coming from this. So basically, I would like to point out that it's going to be a bridge between the user of Aditya L1 and the payload and the science team of Aditya L1 and ISSDC. So ISSDC is the data center and the center at Bangalore, which is going to collect the data from the spacecraft. So data will all be saved in ISSDC. It will get processed with the help of the payload team and payload centers at different parts of India, but it will come back to ISSDC. So our job is not to do anything with the data dissemination or data distributions and so on. Our job at ADS is basically helping people how to utilize this data. So there will be a lot of training things. And also the very important element is Aditya L1 is going to be a space observatory class, mission. So you have to write proposals, and proposals depending on your scientific proposal merit, there will be a time allocation committee who will give you the time. But how do you propose, unless you know the capabilities of different instruments? What science can be done from the instrument is completely dictated by the parameters of the instrument. So user cell will essentially expose or train the user community about the capabilities of the instruments, what kind of data, what kind of volume of data, how you handle this data, and some of the data processing tools and techniques we will be developing and showing. So it's essentially to educate the users to handle the proposal processing system, which will be again developed by ISSDC with the collaboration with the payload team for successful proposal. So focal point for clarifying any queries from users related to proposal submission form. How do it's a help desk, so to say. And to support the payload operations itself. As I mentioned, see, there are different institutions across the India who are going to work as a support payload operation center. And through their coordination, we will be arranging, training sessions in common place to conduct workshop and so on. And then with all this learning, if there is some modifications possible, so this will also help as a feedback mechanism to the instrument team, that whether we can improve on some of the observing systems or observing schemes which we are already pre-planned, because that the pre-planned observations may need to be changed after we learn certain things on space. So this is very similar to what is there as AstroSat support cell at IUCA, and this has been very successful thing. So we will be jointly working with ISRO to maximum utilize the data, develop scientific tools, as I already indicated, and then design and develop required analysis software for handling the data beyond level 2. So the payload operation team will give you the basic, processing, cleaning of the data and all that. But if you want to go beyond that, then we will have, other tool development here. So it's a proposal-driven observatory, as I said, and the payload proposal processing system, which is again developed at ISSDC. It plans to automate the proposal preparation, submission, review process through an online portal. So we will be providing an interface to the user or train the user how to prepare these proposals. And that will also, if the time allocation committee needs also certain help for understanding this proposal system, we will be trying to help in that way as well. So but there are specific tools which will be also doing. We'll be providing catalogs of these CMEs so that people know that such CMEs are been observed. SOHO mission maintains such catalogs, and we will be following their principles, but we are going to do more automated stuff, and artificial AI ML applications will be heavily used in our processing system. You see the raw data from the coronagraph will be looking something like this, but when you process the data and do some image processing only, you will see special features and all that. This is again a classical example. These are again existing space mission data. This is from LASCO example. This is from AIA. This is from Solar Dynamic Observatory, and we will be providing this kind of tools to people. And the idea is, how do we achieve that? We will have short workshops, we will have long workshops, then online sessions, and once or twice the international meetings. So this is our website, Aditya L1 Science Support Cell. It's in a very early phase. This is a workshop which is happening now. You see the exact overlap. Unfortunately, we couldn't change this because it's completely in person, having it in Nainital. I do hope in the next occasion, some of you will be able to join in person as well. You can have a look at the website for the workshop as well. So the future lies in this. So this is a good photograph from our last workshop, which happened in May. And I just wanted to highlight that entire success of this mission is going to be in all of you. And thankfully, I have a big gang of students. So these are termed as Deepu's gang. But I want to extend this gang to beyond Nainital. So I'll be happy to have more people on board. Thank you for your attention.
Thank you so much, Professor Banerjee. So we will now field questions from the audience. So if somebody has them, please ask it directly.
Can I ask a question? This is Dibyendu.
Yeah.
So Deepankar, thank you for a nice overview, particularly to highlighting the Aditya L1 support cell, which I think is going to play an important role beyond just the raw data dissemination that's going to happen. So I understand from the last few slides and remarks that you made that the kind of techniques, let's say, some of us are developing in different parts of the country for data reduction, maybe making some sense of first level data in terms of space weather applications, in principle, can also be hosted at the Aditya L1 data center, where we can perhaps mirror or provide some of the information that we're getting in terms of space weather applications to you, and you also host it. That's also possible in principle, is it?
Absolutely, absolutely. In fact, you have raised a very good point. You see, what happens in India still, a lot of us are
We work in
living
isolation
in
and things don't
isolation.
get canalized. Yeah,
So, and
yeah.
duplication need to be avoided. So,
Right, right,
once we sit together, I'm sure much more thought can be also put into this budget, and we'll be more effective that way.
right, right. No, I'm glad to see this coming up, and I'm sorry that it's we really overlapped this time.
I
And
know.
I
I mean,
hope
I
that some
should
of the
have been
KC
more
people
careful.
can go there next time for the next
Right, right.
workshop.
But it will be a regular exercise now.
Right,
At least 3, 4 workshops in a year will happen for
right.
different durations and different levels of students we will be targeting. Some PhD students, some are for master students, and so on. Yeah.
Okay. Thanks.
Um, there is one question by Sachin Kanodia. He asks, how do the Aditya L1 mission is going to help in understanding the helioseismology in better way?
Okay. So unfortunately, Aditya L1 do not have any specific instrument which is really going to help in the helioseismology result. Just for your information, helioseismology instruments needs velocity measurements on the photospheric surface. So we do not have such velocity measurements of the photospheric surface with such precision, which can improve our knowledge what we are getting from Solar Dynamic Observatory, and previously with SOHO, and also for the Gong network. So there are many such instruments which is available. So really, if one needs to go to the next level of helioseismology, we need a magnetic measurements and velocity measurements at the surface of the sun with a better precision. Unfortunately, Aditya L1 do not have such an instrument. So we will be not really be able to contribute too much in the better understanding of helioseismology.
Um, are there any more questions? We still have a couple of minutes. Okay, so
Yeah.
thank you so much, Professor Banerjee. It was a very informative talk, and I'm sure everybody's waiting for the launch of Aditya L1.
We are
Uh,
all waiting. Yes. Yeah.
Thank you, Deepankar, for taking time out of your schedule. And also, I know that you are very busy with the workshop there. So thanks very much.
Yeah. Thank you.
And
It's
your talk
pleasure.
is recorded and it will be available online for people to see even afterwards.
Oh,
We'll
that's
we'll
great.
we'll
That's great. Yeah.
we'll tell you about
Sure. Sure.
we'll highlight the links and all that.
Sure. Sure.
Okay, take care. Thanks again.
Okay. Bye. Bye. So, with your permission, can
Bye.
I take a
Bye.
leave then? I mean, I will stay myself muted.
Yeah, I understand. We will not hold you. You can leave. Yeah, yeah,
Okay.
sure. Okay.
Okay. Okay. Bye. Bye. Bye.
so our next speaker for this session is Dr. Lakshmi BG. She is a postdoc at the Max Planck Institute for Solar System Research in Germany. She's in the Solar and Stellar Interiors Department. And she is also an alumna of CESI Kolkata. And today she will be giving a talk on can we predict where magnetic active regions are going to emerge on the solar surface. So we can start now if, yeah, hi Lakshmi.
Hello.
It's good to see you.
Yeah, let me try sharing the screen. Can you see the presentation now?
Yes. Okay, so we'll start, but do you want questions now or at the end, like during the talk?
At the end will be better.
Okay, so
Sorry.
if people have questions during the talk, they can type it in the chat box, or they can wait till the end for field of those questions. So, okay, let's start.
Okay. Thank you for the introduction. I will be talking about the emergence of active regions. As the title suggests in the slides, we'll be talking about the properties of flows around around emerging active regions and the studies which are done to predict their emergence. So first, going to the first slide. Okay. So if you look at the structure of the sun, it can be divided into solar interior and the atmosphere. The interior consists of the core where the nuclear reaction takes place. Then comes the radiative zone, tachocline, and the convection zone based on the mode of energy transport. And then comes the solar atmosphere consisting of the photosphere, chromosphere, transition region, and the corona. If you look at the white light images of the sun, we can see what we'll be seeing is the photosphere of the sun, and we'll be at times you'll be able to see dark patches on the surface. These are known as sunspots. So sunspots are regions of large magnetic field which appears on the sun, and if we count the number of sunspots over a period of time, you can see that they have a periodic behavior with a period of 11 years. So this is known as the sunspot cycle. Since these sunspots are regions of large magnetic activity, means that the sun follows a magnetic cycle. So here, if it's a representation of the magnetic cycle, solar cycle 23, where the bright regions represents regions of strong magnetic activity, and we can see that there is a rise in magnetic activity around it peaks around 2001, and then it goes into a minima in the later phase of the cycle. So the origin of the magnetic origin of this magnetic cycle can be explained by the dynamo mechanism, where the initial magnetic field at the base of the convection zone is stretched by the differential rotation. So the convective zone of the sun rotates differentially. That means the equator rotates faster compared to the poles. So this differential rotation stretches the magnetic field in the toroidal direction, and this field lines, due to magnetic buoyancy, they rise through the convection zone and penetrates through the solar surface, forming bipolar active regions. These active regions later decay, and the magnetic flux gets diffused and advected towards the poles of the sun by flows along the north-south direction known as meridional flows, leading to a generation of magnetic field for the next cycle. So these magnetic field lines, which penetrate through the convection zone, gets acted upon by the turbulent convective motions of plasma in the interior, and they can twist the field lines. These twisted field lines gain high non-potentiality, and this leads to the buildup of magnetic energy, and these field lines become highly unstable. So these instabilities leads to a magnetic reconnection, which can release huge amount of energy in the form of flares and CMEs. So this is just a pictorial representation of the various aspects which are affected of our life, affected by this high energetic events. It can affect both the life on Earth and space. So it's very important to understand the origin of these events, and as we know, these are generated by the active regions, the highly magnetic active regions. So it's essential to understand the origin of these active regions, and also to develop prediction methods to predict their emergence, so that we can prepare ourselves to face these kind of events. But there's an issue. The observations what we have of the sun are constrained to the solar surface or to the atmosphere. So we cannot look into the interior. We don't have observations of the solar interior. So we need a way out of this. For that, we can depend on some tools like the helioseismology. So if you look at the surface of the sun, like in the Doppler, in the video shown here, which is generated by stacking Doppler images of the sun over a period of time, you can see that the surface of the sun is always in an oscillatory motion. This is because due to the convective motion in the solar interior, acoustic waves are generated. And these waves, like in the cartoon shown here, when they move towards the surface of the sun, gains high velocity because of the drop in density. And these waves, because of the increase in the velocity, they are reflected back to the solar interior. And once these waves, they travel to a solar interior, there is again rise in temperature, because of which the velocity again increases and they're reflected back to the surface. So this back and forth motion of these waves in the solar interior results in the oscillatory motion which we observe on the surface. So the waves, these waves will have the signatures of the properties of the medium through which it propagates. So if we try to understand, or if you look at the properties of this wave, we will be able to understand the properties of the medium, the magnetic field and the velocity of the medium through which it's propagating. That means the convection zone. So there are various methods developed to understand the properties of the of flows and magnetic field in the medium. For studying the local variations in this flows and magnetic field, time distance, local helioseismic methods were developed, which includes time distance, ring diagram analysis, holography, etc. So this is just a list of studies done using these methods. So using these methods, we can look at the local variations of flows around regions of strong magnetic activity. So like in the map shown here, it's for Carrington rotation 1949. The horizontal flows is the flows along the in the north-south direction and along the east-west direction of the sun. So these velocities, which are computed for this Carrington rotation, and it's seen that these velocities converge towards regions of strong magnetic activity. These regions of strong magnetic regions are represented by this shaded area here. Now, that means the local flows converge towards regions of large magnetic field. Now, if you look at another case study of one particular active region, flows around one particular active region, we can see that the flows are converging towards the active region for the near surface layers. And once we go deeper, it starts diverging. So the various studies following this were done to understand the flow properties around the active regions after the emergence. So it's natural to think whether this flow properties change, or whether they will have signatures of emerging active regions. So whether they will have any perturbations before the active region actually emerges on the surface. So one of the initial searches for helioseismic signatures of rising flux tubes or rising active regions were done by Kosavishev et al. In 2000, where they looked at the perturbations in the plasma wave, in the acoustic wave speed around an emerging active region for over a period of 1 day prior to the emergence. So here, this in the first panel represents the wave speed perturbation as a function of depth and longitude. The active region is present at the center of the box, and the top slice represents the magnetic field. And here we can see in the first panel, there is no significant variation in the acoustic speed is observed. But when you go like maybe around 12 hours prior to the emergence, there are slight signatures already present in the slight perturbations already present in the acoustic wave speed. So maybe a couple of hours prior to the emergence, these perturbations become strong and it covers the whole depth range. Later, after the emergence, we can see that these perturbations become strong and their amplitude grows with the rise in the magnetic field strength. So here we can see that slight signatures of emergence are actually seen in this wave speed around like 12 hours prior to the emergence. So, but when there is no significant time difference observed between the actual presence of like strong perturbations over the whole depth range and the evolution of magnetic field or the emergence of the magnetic field. This is because the magnetic field emerges.
Just a quick clarification. Is this result something that is robust in the sense that other groups have been able to get this, or this is unique?
This was the initial try, but then this was continued by other groups using the velocity measurements, which I will be showing in the next slides. So this was just with the acoustic velocity.
This is Dhruvo.
Yes.
Hi, can I ask a quick thing? So
Yeah.
this is not really a change in the dispersion relation. This is like a flow, is it?
Yeah.
Thanks.
This is so this signature was actually seen in the velocities after the inversions, which you can see in the next slides.
Hi, Lakshmi. This is Srijan. Can you hear me?
Yeah.
So for this plot, it's not quite clear what the depth is. Can you just point out the maximum depth?
It's still 18 mm.
18 megameters.
Yeah.
Okay. All right. Thanks.
So later, some studies were done using the horizontal flow velocities computed using ring diagram analysis. So Gom et al. In 2011 computed the horizontal velocities of 68 active regions, emerging active regions, and computed the vertical velocities around these regions and tracked them over time. It was observed that the vertical velocity shows an upflow given by given by this blue region at depths greater than 12 mm, and this upflows starts increasing with time, and they becomes large even after emergence. Later, a downflow is observed for the near surface layers 4 to 10 mm after the emergence was also observed. So, sorry. Later, studies by another group, Birch et al. 2013, using again helios flow measurements, horizontal flow measurements surrounding emerging active regions, had also shown that there are converging flows towards the regions of emergence one day prior to the emergence. So this was after I have mentioned about the studies done using the wave velocities and the plasma flow velocities. So later, studies were done to compute the travel times of waves around regions of emerging active regions. Like the travel times around 107 pre-emergent samples were computed. So in the first row represents the magnetic field of these active regions one day prior to emergence, and you can see that the magnetic field varies over the day and but very slowly. Then the second row represents the average travel time. Yes.
Sorry. Which component of the magnetic field?
So this is the BR component.
The vertical component.
Yeah.
Thanks.
So later, the mean travel times were computed, and it shows that the mean travel times especially correlated with the vertical component of magnetic field. The east-west and the north-south travel time differences also shows variations with the magnetic field strength, and there is an asymmetry observed in this travel times, which may point to the convergence of plasma flows towards the active regions. So from this study also, it's clear that there are signatures observed in the wave travel times one day prior to the emergence, and statistically significant differences are observed. And this was verified by using a sample of repeating the analysis for a sample of quiet sun areas too.
Lakshmi.
Yes.
Sorry, I think this is maybe it's just my naivety. It's not clear to me at all what is happening here. Could you explain?
It's like signatures in the travel time differences were seen, which are in phase with the magnetic field strength. This is like 24 hours prior to the emergence.
Right.
So here in the second row, you can see that there are slight signatures in the travel time differences, which are also spatially correlated.
When I see yellow and blue,
yeah,
then I basically think that this is how travel times are different from what? Difference between which travel times?
So this is the travel times along the north-south and they have computed the travel time differences along the north-south direction and along the east-west direction. And the second row represents the mean travel time differences, mean of these two travel time differences.
And the last one?
The last one is the travel time difference along north-south direction.
Okay, thank you.
Yeah. So in the most...
If you want to take a break at any point in time, get some hot water or tea, please do that.
Yeah,
I know
yeah.
that you are unwell. Thank you for still giving the talk, but feel free to take a break if you want to for your throat.
It's okay. I'm having tea. Thank you. So later, in the most recent study, the horizontal velocities around emerging active regions were computed, and the divergence of plasma flows around these active regions are shown in these pictures. Here you can see that the active region, the emerging location, is given by these white circled areas, and the velocities are represented by the arrows. Here, around 35 hours prior to the emergence, there is no structure actually seen. But like 24 hours prior to the emergence, you can see that the flow starts converging towards the east side of emergence, and the flows are retrograde in direction. That means it's towards the opposite to the direction of rotation. Now, these converging flows increases, the magnitude of these converging flows increases with time, and it is centered to the east of the emergence. Later, like a couple of hours prior to the emergence, these converging flows are still present, and a prograde flow starts appearing, which extends to the leading polarity. So here also we can see that signatures of emergence starts appearing like 1 day prior to the emergence. So there are other studies which again looked at various properties of wave and plasma velocities, and have seen that helioseismic precursor of emergence are observed 1 day prior to the emergence. So these velocities which were computed around the active region emergence were using helioseismic methods, but the velocities obtained using local correlation tracking had also shown signatures and are in agreement with the helioseismic observations. So shown in Birch et al. 2019. And theoretical studies have shown that the dominant effect on wave propagation is a result of retrograde flow associated with the rising flux tubes. These are done using flux tube simulations by Birch et al. In 2010. So, but there are various limitations for these helioseismic observations. The first and major limitation is the value of perturbation. The perturbations are very small, and because of which, to get a statistically significant result or to have a high signal to noise ratio, averaging over large number of samples are needed. So here also in the previous studies which I have mentioned, averaging over around 105 emerging active regions were done to get statistically significant results. So again, because of the small values of perturbations, if you take particular case studies of the flow or wave properties around a particular active region, for the same active region using different methods have given contradictory results. Another factor is that here the presence of surface magnetic fields or the remnant fields from the decayed active regions are not considered in these studies. So the presence of these fields can complicate the interpretation of the signal, which we think as pre-emergence signals. Again, there are constraints on tracking because if the active region is emerging towards a limb, then we cannot track them well, and also the systematic effects will be larger at these towards these sites.
Lakshmi,
Yes.
just to be clear,
Yeah.
so these flow fields are calculated by inversion, which
Yes.
uses a kernel, and the kernel actually doesn't have any magnetic field in it.
Yeah.
Thank you.
So this means that we will have to look for alternate approaches to find methods to predict the emergence of active regions. So one way is to look at the magnetic field or the velocity images of the surface of the sun. So like in the image shown here, this dashed line represents the a region of emergence. The magnetic field and the velocity images are given. So prior to the emergence, there are slight signatures of magnetic field, and also in the velocity, there are downflows or upflows, which are given by dark areas are observed. So with time, when the magnetic field starts increasing, this downflows also increases in amplitude, and then this white upflows also start increasing in amplitude, and then their downflows also starts appearing, which are given by this white shaded area. So after the emergence, you can see that upflows are present towards the leading polarity of the active region, and the downflows are present towards the trailing polarity of active region. But this is like a couple of hours only before the emergence. But with naked eye, we won't be able to see any kind of signatures like this if you are looking at these images one day prior to the emergence. So because of this issue, we'll have to depend on some tools like machine learning to look for features on these kind of images and look for signatures of emergence one day prior or like a few days prior to the emergence. For this is as part of the SESI-SPARC project, Vishal Singh had done some initial trials using feature identification, using convolutional neural network. I'm not an expert in this, but I would like to mention the work which he has done with the initial trials which he has done for this purpose. So, sorry. 382 active regions, which included both emerging and regions with emergence and no emergence, were selected from both the hemispheres, and the corresponding HMI doublegograms for these regions were selected. These regions were tracked for 3+1 days, which means 3 days prior to the emergence and 1 day post-emergence. And these regions were constrained between ±45 degrees from the central meridian. This is to reduce the systematic effects and systematic effects from impact of systematic effects on the velocities. Then these maps were postal projected and are used in a convolutional neural network. So two methods were used for this purpose. One is single image and another is snapshot extraction from time series. So for the single image method, doublegograms at the time of emergence were fed to a neural network with a training to test ratio of 70:30. The neural network creates feature maps, and then they attempt to distinguish between images with and without emergence in this case. And then for the next method, it used snapshot extraction. So for this method, I used doublegograms, which are tracked for 3+1 days with 30-minute cadence. And for snapshots, and then an attempt was made to extract meaningful information by using snapshots from the time series. So the snapshot used here was a variance of each pixel from each pixel across the time series. So the results from these two analyses are given here, but the mean accuracy is very low in both the cases. So we cannot derive any conclusions from this analysis, but it's just a trial. We have still hope like we can improve this method because we still haven't used the information from magnetograms and intensity maps. So these in magnetogram and intensity maps also will have signatures, like I have shown in the first slide. In the previous slide, there are signatures of these emerging fields in the magnetogram. So including this magnetic magnetic field and intensity map information can improve the results, may be able to improve the results. Then another track is like by using helioseismic parameters obtained from helioseismic analysis. Like we have seen, as I've mentioned in the previous slides, there are already signatures of emergence seen in the parameters obtained from helioseismology. But this will need a large computation time, and then the constraints the constraints related to the method which we are using for the analysis. All these needs to be considered before we choose them for machine learning purpose. And another thing, most important thing, is choosing a proper neural network for handling time series. So we are still not sure whether the method used here was really good for handling the time series with which we are dealing with. So maybe the experts present in this workshop will be able to guide us in this problem. So this is what I wanted to talk about: the emergence of active regions, the issues with predicting the emergence of active regions, and the initial work done by the Spark team for using machine learning to predict their emergence. I would like to thank the organizers for inviting me to give the talk, and also the SESI Spark team for making me part of this project. And thank you. Thank you for listening.
Thank you so much, Dr. Lakshmi. It was a great talk, and we already have questions from the audience in the chat box. So the first question is from Ashwin Amirtha Raj. So they ask that since at the maxima, the surface magnetic field gets increased due to the presence of more sunspot, does it affect the prediction more? If so, helioseismic method to predict the emergence in active sun at maxima is less useful.
So the issue is when there are overlapping regions, or like if you are using helioseismology, the issue will be whether we are able to constrain the regions which we are choosing for emergence. So if there are already active regions present near to the location which we are choosing, then the magnetic field from those regions can obviously affect the region, the parameters obtained from the analysis of our chosen regions. Yeah, so this is an issue. So even that needs to be analyzed, like what is the effect of. So that's a problem with helioseismology. So maybe that's why we wanted to look for take help from machine learning algorithms to do this. Because if you are just looking at the helioseismic methods, then of course, like Dhruva was mentioning, the kernels will get affected because of the presence of near surface or magnetic field in the neighboring regions. So yeah, it will be difficult to predict in that case, because we won't be able to isolate the regions.
I hope, okay. I think there is a continuing question from Ashwin. So does the same signatures can be found on the emergence occurred without sunspot association?
So here, for the analysis which are done are for regions with sunspots. So I'm not sure, have to say, I don't know whether anything was seen for regions without association. So yeah, well, the regions chosen for the analysis here were only for particular sunspots, and also without no emergence or no sunspots.
I have a question, Om. Can I ask?
Yeah, sure, go
So,
on.
Lakshmi, am I correct in understanding that all the evidence of pre-emergence signatures that you showed are basically a few hours before the actual emergence, or maybe at best 1 day before emergence?
Yes.
And there is, so basically what you're saying is that even if you can predict emergence, there's going to be, with the current techniques, the window is 24 hours and not before that.
Yes, for all the studies which are done till now, it's all the signatures were observed 1 day prior to, like maximum 24 hours prior to the emergence. If you
And
go beyond.
how much processing is required to get this? Can this be done? I mean, are these all post facto studies, or were there successful predictions of emergence before an active region emerge? Is there anything like that?
No, here in all these cases, which I have talked about,
Post-emergent studies. Okay, hindcasting. Sorry.
it's like averaging is done over a large set of active regions. So not for any particular the issue with case studies is like if you're considering one particular active region using different methods, people were obtaining different contradictory results. So that's why they to get statistically significant signatures of emergence, large averaging had to be done, or large
So
samples.
let me make this question more specific. Currently, anywhere in the world, is there any technique that can predict the emergence of an active region before it has actually happened, or such a technique doesn't exist?
No, as far as my knowledge, no, not till now.
All right. Okay, thanks.
So we have a question from Chitradeep, who asks that we know that the mean tilt imparted to any active region essentially due to the local vertical motion induced by the Coriolis effect. Do helioseismic observations capture any local vorticities within the convection zone?
Yeah, helioseismic methods have helped in computing the vorticities around active regions. So once you have the helioseismology gives the horizontal velocity component. So once you have the horizontal velocity components, then you can obviously calculate the vorticities around those regions. So yeah, it's done already. It's an established thing.
Okay, so I think we have one more question from Shavik Roy. Please go on, Shavik.
Hi, Lakshmi. This is Srijan. I'm just sitting with Shavik.
Okay.
So the question is, you mentioned that there is this averaging over active regions that you do, right? All right, that's traditionally done, and that's over different active regions, right?
Yeah.
So why would you expect some averaging across different active regions which have like different geometrical structure to give you something which has a common property, right? That's my first question.
Okay.
It's not like a sunspot which is circular to some approximation. So an active region can have very different structures, right?
Yeah. So that's actually a problem because, like I said, I've mentioned the geographic location of the active regions and the neighboring effects of the neighboring flows will actually affect the results what we are seeing. So yeah, here they have done this averaging just to reduce the signal to noise ratio, but I'm also not very sure like how these properties will be on averaging whether we are actually losing some information.
Mm-hmm. So the other question that I have is from this image that you showed from Kosovo 2000.
Mm-hmm.
Those are sound speed perturbations, right?
Yeah.
But it's kind of known that sound speed perturbations and magnetic field anomalies are to some extent entangled, meaning when you perform an inversion, you cannot really tell one from the other because they have similar signatures on the observation. Do you know how far they have claimed these to be purely sound speed anomalies or perturbations and not magnetic?
I'm not. I don't do inversion, so I'm not very much aware about this issue which you are talking about. But yeah, in the paper, in the Kosovo et al., it's an initial work where they have actually claimed this as a wave speed perturbations. So,
okay.
Yeah.
Okay. Thank you so much. That was very nice.
Thank you.
I don't think we have any more questions. So I would like to thank Dr. Lakshmi for the wonderful presentation and also for fielding so many questions. And thank you. And
you.
we have ended today's session a bit early, but we hope that everyone would join us for tomorrow's session. And I bid you good night on behalf of Sesiazer Kolkata and the Spark team. So let's meet
Thank you,
tomorrow.
Om. And Lakshmi, thank you very much for coming in spite of not being perfectly health-wise.
Thank you.
I'm on the road, so I can't really show my face because I'm sitting in the car. It's dark here. But I look forward to having a discussion with you, Dhruva and Srijan. I think Friday most likely is the most likely possibility. While Srijan is still here, and yeah, we can drag him in. Thanks very much.
Sure.
I really enjoyed your overview. I think that was very nice talk.
Thank you.
Okay, bye bye, and take care of your health.
Thank you. Bye.